Hello and welcome in this natural convection series. So I have completed two lectures, and in those two lectures, firstly I have introduced you with the natural convection, that from where this natural convection arises and what is so natural about this thing, right? And what is so unnatural about the other things other than the natural convection, like the forced convection and all other things. And in the next lecture, I have introduced you with the problem of a vertical flat plate, and we derived these equations of governing equations, right? So these are the governing equations, and after applying the boundary layer assumptions, so we assume that this heated layer, okay, and I also told you that this is a heated layer and this is something beyond or something more broad compared to the boundary layer, that is the thermal or velocity boundary layer, and here we call it a heated layer. But we will think, sorry, we will see that based on the Prandtl number of the fluid, we can distinct the layers for velocity variation and the temperature variation. So for some case, the thickness along which the velocity variation will be there, that will coincide with the thickness along which the temperature variation will be there. But for a particular case of Prandtl number, you will see that the velocity variation can go beyond the thickness where the temperature variation is important. Okay, and that is physically also very much, that can be perceptible from the physical reasoning also, that I will show you. So without any delay, let me proceed with the following things. Firstly, on these things, okay, that is the set of governing equations that we obtained after applying the boundary layer assumption. Now we will apply something called a Boussinesq, okay, approximation. Now those of you who have studied turbulence, please do not confuse this with Boussinesq hypothesis. Okay, so this is not Boussinesq hypothesis in turbulence. So in turbulence, Boussinesq hypothesis, what does it do is it correlates the the Reynolds stress, that is tau r, okay, to the mean velocities. Okay, so there we define something like this, that is the turbulent viscosity, okay, into du bar del ux, sorry, del uy, and this is this thing, okay, plus there is another term, okay, minus Kronecker delta, okay, ij, or I can write also xy, okay, Kronecker delta x bar y bar into 2 by 3, okay, into the turbulent kinetic energy, kT I can write. Okay, so these things arise. Clear? Now this is the Boussinesq hypothesis. I just told this, because I want to make you clear that whenever you are studying natural convection, never ever say that you are applying the Boussinesq hypothesis. That is totally a different thing. So if you are appearing for any interview and you use this term, then they will catch you. Okay, so although you are maybe thinking the right thing, that is the Boussinesq approximation, but if you tell them that I am applying Boussinesq hypothesis, then it is wrong. Okay, so now what is Boussinesq approximation? So let us copy just the x momentum equation. Okay, so Let me copy this and paste this. Okay, and I will also write that this is my x momentum equation. Clear? So this is my x momentum equation. Now in this equation we have rho in mainly two places. Firstly, we have rho in the inertial term and we have rho in the this term. Okay, that is the body force term. Clear? So now what we will do is, firstly we know that what will be our dp dx, dp infinity dx. So P infinity is what? P infinity is the ambient pressure, right? Ambient pressure. Now, is the ambient fluid moving by any means? No, right? So the ambient fluid is at the static condition, and that means dp infinity dx will be minus rho gx. And what is our x direction? It is pointing vertically above, so it is minus rho g. Clear? That means this term will be minus dp dx, dp infinity dx will be plus rho g. Clear? Or I should write that rho infinity into g. That is, it is rho infinity means it is the density of the ambient fluid. Clear? Or you can also write this as rho r into g, that is the reference density, because I have declared already that our reference state is the ambient state. Okay. If you do not declare that, then you cannot write that your rho infinity is equal to rho r into g. I mean rho infinity is equal to rho r. Okay. So now this governing equation becomes rho u, this one is equal to so I can take this g common and I can write this one, right? Okay, plus this thing. So this I can write. Now I can ask you a question that we have two types of rho here, rho and rho r. Okay, now this rho can actually be a function of both t and p, but I have already shown you that for low Mach number flows we can assume that this is only a function of temperature and not the function of pressure. Clear? So now tell me, or firstly I should directly write it as rho infinity. Clear? So now tell me that I can write both of these rhos as rho is equal to rho infinity into 1 minus beta t minus t infinity, right? From this equation I have already derived it, right? For low Mach number, obviously that will be beta infinity. Okay, right? So if I put this, then here also this rho becomes a function of temperature. Okay, and the analysis will be very much complex. That is why our dear scientist Buzinesk put the approximation that, my friend, because it is natural convection, we have to keep this term, because this is the term that is driving the flow, and loosely we call this as a buoyancy force per unit volume, because all these terms are having the units of force per unit volume. That is why this term we loosely call as buoyancy force per unit volume. And Buzinesk was a scientist, and that is why he observed that if we drop out this term, then there will be no natural convection. That is why here we cannot consider that this rho is a constant and is equal to rho infinity. And that is why he said that okay, we don't want to drop out the problem. That is why we will consider that this rho is a function of temperature, but this rho is a constant. So this has no more logic. Okay, this is a assumptions only. Okay, this is an assumption or approximation only. Now this is the beauty of engineering. Now at this point any mathematician can jump up and argue with me that how can you do this? I mean, ऐसा कैसे कर दिया अचानक से, एक रो को कांस्टेंट मान लिया, दूसरे रो को वेरी करा रहे हो. Okay, but engineers, okay, we are engineers and we care about making the equations work for us, to make the things that will work for us. Okay, so roughly I can tell you that you have to produce something that you can sell to the world. Okay, that is the basic job of an engineer. If you are in a company, no one cares about second law of thermodynamics, no one cares about the fluid mechanics. If you can make the thing work by hook or by crook, then you are an engineer, you are a capable engineer. So this is why we take such approximations, and you always strive for these things because there are so many unsolved problems. Unsolved problems means analytically unsolved problems. Okay, we have now the tools like ANSYS, COMSOL, but if you can give any approximate analytical solution that will simplify our life, then honestly you are a genius. Okay, for that world will not ask you that how can you put this type of approximations. If you can show that I have taken this approximation and this is matching the experimental or the numerical results, if this approximation is matching those results, then you are accepted, you are done. Okay, so these kind of thinkings are very important, because if we think like it that no, I am a mathematician, I love mathematics, I can't allow this kind of assumptions in my subjects, then don't study engineering. Okay, so if I allow this assumption, Boussinesq approximation, then this equation will be rho infinity into del q del x plus this one. Okay, and now this will be what? This will be minus, okay, and ultimately actually I am just writing this term first, and we will be getting what? We will be getting plus g beta infinity t minus t infinity into rho infinity, right? Into rho infinity. Okay, so this is the final x momentum equation after applying the Boussinesq approximation. Let us see that what will be the y momentum equation. Honestly, it will not have any kind of change, so it will be del p del y equal to 0, and let us say the energy equation now. Okay, so okay, let me also write the continuity to maintain the flow. Okay, continuity is del q del x plus del v del y equal to 0, and we have the energy equation. Clear? So energy equation says that u del t del x plus v del t del y is equal to, okay, alpha del 2t del y2, right? I think I have written the right thing. And okay, so previously this, in the previous lecture I made a mistake that I have put rho here and alpha here. No, if alpha is here I cannot put rho there. Okay, so now if someone asks you that what is the Boussinesq approximation, you have to tell that rho is variable only in the buoyancy term. Okay, only in the, or you can also say body force term. Okay, and everywhere, uh, everywhere. Okay, so else, I mean, I should convert it into any other color. Okay, I will convert it. Everywhere else, rho, mu, alpha, these all are constant. Constant. So let me just change the color of this statement to make it stand out. Okay, so color can be green. Fine. इनका कलर क्यों चेंज हो गया? Okay. Now, so these are our final equations. Fine. So what can we do with this equation? बहुत कुछ तो मिल गया. अब देखते हैं. Now let us analyze. Okay. For this particular problem of the vertical plate, vertical isothermal plate, let us analyze this problem. I will again copy this x momentum equation. Okay. So this should be actually your mentality. Okay, that if you are given any kind of problem, be it the problem of the fluid mechanics, heat transfer, solid mechanics, try to obtain the governing equation first by simplifying the most general form of the governing equations you have. Okay, so here in fluid mechanics, Navier-Stokes, or I should say, actually for the continuum mechanics, Cauchy-Navier equation is the most general equation. Okay, only assumption is that the continuum hypothesis is valid. That is why it is applicable for our continuum. Okay, now from that we obtain the Navier-Stokes equation. For a fluid. Then from Navier-Stokes equation we have derived this equation after applying so many assumptions, right? So this should be your thinking, especially if you want to pursue higher studies or research. Okay, so now let us do one thing. So if you have already done, and I assume that you have done the course on the forced convection, okay, or the external or internal forced convection, and if you have already seen my YouTube videos, my lecture series, or any other good lecture series, then you know that what is order of magnitude analysis, right? So let us do the order of magnitude analysis of x momentum equation. So let me write it here. So the order of magnitude analysis of x momentum equation. Okay. Now, before doing anything, why do we do the order of magnitude analysis? We want to know that if we can drop out any of the terms or not, or there can be any other objectives also. That means maybe we know the order of magnitudes of other terms, but we don't know the order of magnitude of a particular term, and we want to know that, and that is why we are doing the order of magnitude analysis. Clear? Now here, can you tell me that which term for sure I cannot drop? Think. I will pause for some seconds, or obviously you can also pause the video. Obviously that term is this one. Okay, because see, Boussinesq has done so many things. Boussinesq has thought so many things that I cannot drop out I cannot take the density constant for this term. Okay, so that means this term has something special, and obviously this is the term governing the flow, so we cannot drop this term. So this is of the order of G beta infinity some delta T reference into rho infinity. Okay, this is almost like a constant, and you can say that this del T, I should say del Tc, okay, I mean characteristic temperature difference, and to be very clear, this del Tc, this I should write as T wall minus T infinity. Okay, I think I have denoted the wall temperature by T surface, Ts. Okay, so to make the, I mean for the sake of consistency, I should write it Ts. Okay, fine. Now what is the order of magnitude of this term? Okay, so let me write it with other color. This will be of the order of mu. Okay, something uc that we don't know, but our domain of interest is the heated layer. Okay, I have denoted the heated layer by delta, only delta, right? So okay, so I say that my delta is of the order of delta naught, so this will be delta naught square. Okay, if you are getting much trouble understanding these things, that how I am getting this mu into uc by delta naught square, I just suggest you to go back to the convection lectures. Okay, because already I have declared that you must have studied the forced convections. Okay, and before, or at least the boundary layer theory. In the boundary layer theory also, at least, I mean actually I have taught the boundary layer in this forced convection lecture series also. The full boundary layer I have taught, almost the full boundary layer. Okay, that is required for the forced convection. Okay, now this part let us see. Okay, now I mean let me do the analysis for the separate terms. So firstly I will multiply the rho infinity with each term. Okay, so for this term, the first term, this will be of the order of rho infinity uc square by L, that is xc is L, that is the length of the plate. Okay, finally this term is of the order of rho infinity vc uc by delta naught. Clear? Okay, so now we are sure that we cannot drop this special term. Okay, and if I also write the name of this special term, because if you are appearing for GATE, I can remember that in the year in which I appeared for GATE, in GATE 2023, they asked that in this governing equation which term is representing, is I mean representing the which term is representing the buoyancy force. Okay, they asked, so you must know. So this is the I will write this with any other unique color, and that can be this. Okay, so this is too much light. Okay, red I have also used which color. Okay, violet is fine. So this is called, okay, this is called the buoyancy. Okay, this is called the buoyancy term. Clear? If the spelling of the buoyancy is wrong, I apologize for that. Now this is the obviously viscous term, and this is, and I mean both of these are the inertial terms. Okay, so now let us go to the order of magnitude analysis of continuity. Okay, so order of magnitude analysis of continuity. I could have skipped this, but still, for the sake of continuity itself, continuity in the teaching, I have to do it. So this term has the order of UC by L, and this term has the order of VC by delta naught. Now we don't have any other term in this equation. That means UC by delta L has to be of the order of VC by infinity. That means VC is of the order of UC into delta L by, UC into delta naught by L. Okay. Now if I put this VC here, this VC here, then you will see that this term also becomes same as this term. That means the total inertial term has the order of magnitude of rho infinity to UC square by L. This I have shown in the convection lecture series also. Okay. So we have essentially three type of terms: inertial term, viscous term, and the buoyancy term. Okay. Now there can be various situations based on which we will divide the problem. Okay. Now here buoyancy term must be important. Okay. Buoyancy term must be important. Now the comparison will be between this term and this term. That will define that which class of problem you are solving for this particular problem. So let me show you that what I am trying to say. So firstly, again, okay, I don't want to write again and again the same words, so sorry. Now order of magnitude analysis of the energy equation. Okay. Energy equation. Okay. So what is energy equation? U into del T del X plus V into del T del Y is equal to this thing. This is very easy. Now what will be the order of magnitude of this term? This will be UC, okay, UC delta TC by L. Order of magnitude of this term VC, okay, and delta TC by delta naught. Order of, okay, so following the tradition I should change the color. Okay, and finally what will be this term? Is of the order of alpha delta TC by delta naught square. Okay, and we know that this UC by L is of the same order of VC by delta naught. Okay, that means both of this term I can write as order of UC by L into delta TC. Clear? Okay. So now that means again here we have two type of terms. So I can also write this, that this is like advection terms and this is the conduction term. Okay, it is like the fact that the energy that is being conducted from the wall, that has to be advected from by the fluid to avoid any accumulation of the energy. Okay, because it is an unsteady state problem. Now if we have only two kind of terms like the continuity equation, UC by L into TC, that must be equal to alpha delta TC by this thing. Okay, that means your UC becomes of the order of alpha L by delta naught square. This is very important. So this is one velocity scale that you are getting in terms of delta naught, and delta naught is the representative of the of the buoyancy force. Delta naught is the representative of the buoyancy force. That means we are clear that our UC, that is the velocity that we are getting because of the natural convection, is actually governed by the buoyancy effect only. Okay, so I think I have not made any silly mistake. Okay, fine. So if this is now our UC, now let us proceed. Okay, now in this equation, firstly let me copy this equation. Okay, copy this whole thing. Okay, order of magnitude of this thing. Let me just copy this. I will need this thing. Let me make it a bit smaller. Okay, fine. So here now we will see we have two options. Okay, here we have two options. So here if I call this as my term 1, that is T1, this as my term 2, this as my term 3. Okay, or I should write directly I, that is the inertial term, V, that is the viscous term, and B, that is the buoyancy term. So I will write here that my B is always important in this governing equation. Now the competition is between, okay, competition is between this and this, I and V. Okay, I just tried to, okay, nice. So they are fighting, clear, they are fighting. Thak, 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 thak. Now this I and V are fighting. Okay, and between them let's see that who will win in which case. Okay, so option 1. Okay, firstly let me derive the condition. Let us see that what is I by V. So I is of the order of this thing and V is of the order of this thing, UC by delta naught square, but UC is something that we don't know. Okay, so here first of all let us simplify this. Rho delta naught square, okay, rho delta naught square by mu L into UC. I think I have not made any mistake. Okay, and this UC now we will use. Okay, that is alpha L by delta naught square. Clear? So this will be alpha L by delta naught square. So now that means this becomes rho this into alpha L, cancelled out, L will be cancelled out, So this is obviously mu infinity because we have applied the Boussinesq approximation. These all mu's are mu infinity and these are constant. So alpha by mu infinity by rho infinity, or and there is also alpha infinity. So alpha infinity by nu infinity, that is 1 by PR infinity, Prandtl number for the ambient state. So that means we have inertia by viscous of the order of 1 by Prandtl number based on the reference state, right? Therefore, it is very clear that if my Prandtl number is much greater than 1, then I will have, sorry about that, I have to reduce my pen thickness. Okay. You can just skip this part in the video. Okay. It is 2.5, it is 2.5, to convert this also. Okay. So this means, clearly, this means that my inertia force is negligible compared to the viscous force, right? Because pendulum, sorry about that. Okay, and if I have this, this would mean that I will now neglect the viscous forces, and if I have a fluid with Prandtl number at the infinity state or the reference state with of the order of 1, then I have to take care of both the terms, inertia and viscous. Now let us take these cases one by one. So the first case, okay, case 1 is Prandtl number much greater than 1, and that means we know that we will neglect the inertia. Clear? We will neglect the inertia. Now I have already told that we cannot neglect the buoyancy term, right? Then there is no question of natural convection. So here we will neglect the inertia term, okay? Because Prandtl number is much greater than 1, we will neglect the inertia term, and that means this viscous term will compete with this buoyancy term. Okay, so if the viscous term competes with the buoyancy term, then these two things will be, these two things will have the same order of magnitude. Okay, so that means if I just copy these two or this whole thing, okay, I'll just copy it and I will just paste it here. Okay, so now from this I will be having that my mu uc by delta naught square is of the order of g beta, that is it at the infinity state, delta tc, and now I will write this, that is ts minus t infinity into rho infinity. Clear? Okay, another term. So see, here we have two things which are not constant. Okay, and what are those two? This uc and delta naught. So what do I mean by not constant? That is, these parameters are either of those of fluid or that of the plate. Okay, but these things will be governed by these parameters. Okay, now we have to estimate these things, and further, as engineers, we have to estimate the heat transfer from the plate. Okay, so the main objective to estimate the heat transfer, and as I assume that you have already gone through the forced convection courses, then you must be knowing that what is Nusselt number. So this Nusselt number is nothing but, okay, h NuL based on a characteristic length L, HL by K, and this K is K of fluid, right? So now that means if I have to find the heat transfer, I need to find the H. If I have to find the H, I have to find the Nusselt number. Then now my goal is to express Nusselt number in the in terms of these parameters, okay, parameters of the fluid and the solid plate. Clear? So let us see that how can we do that. Okay, so first of all, here as I told earlier that we have these two parameters which are dependent on the plate and fluid parameters.
So we, I mean, so I can say that these are uh, type of unknowns. Okay, now I need one more equation, and that equation is this. See here also, alpha and L are the parameters of the plate and fluid, but these are the unknown parameters. So I will just again copy it. Okay, and I will just place it here. Okay, okay, this, and again this equation. Okay, I will just copy it and place it here. Okay, so these two master equation we are having. Okay, I will just box them. Okay, so these two. Now from these two we can, now I will just estimate this un, I mean uc, okay, in terms of the given parameters. So how can I do that? From this equation, so if I say that this is my equation a, this is my equation b, so from a I will get what? From a I will get my delta naught square, and that is of the order of alpha L by uc. Okay, so if I now use this thing in the b, then I will get mu uc by alpha L by uc. I will take that uc on the numerator, and this will become j beta infinity ts minus t infinity into rho infinity. And now my uc square is g beta infinity ts minus t infinity rho infinity alpha infinity L by mu infinity, right? So actually these mu's and alphas are at the reference state infinity. Okay, so now I got the u scale as this to the power half. Okay, so this is my velocity scale. Okay, for the case that is I mean for the case of very low, sorry, very high Prandtl number, right? Very high Prandtl number. Okay, now let us find that for the delta naught estimation for the delta naught. So again from equation a we will get uc is of the order of alpha L by delta naught square, and if I use this in the equation b, then I will have mu infinity uh, uc, and now I have to put in instead of uc I will put this by delta to the power 4. This is of the order of g beta infinity ts minus t infinity into rho infinity. Okay, I hope I am not making any silly mistake. So now this will mean that delta infinity to the power 4 is of the order of mu infinity alpha L by g beta ts minus t infinity rho infinity. Clear? So now that means I can write my delta naught is of the order of g beta naught ts minus t infinity, okay, by what? By, now this mu by rho is actually nu. So nu infinity alpha infinity by L, okay, whole to the power minus 1 by 4. So my battery is dying down. I have to close this very soon. Don't worry, I will obviously continue this series. So now if I have to find the scale for Nusselt number, so that will be HL by K, right? Now this is of the order of H delta naught by K into uh, what? L by delta naught. Now we can prove that this is actually of the order of 1. How we can prove? I have proved this for multiple times in the forced convection thing, but still at the wall we have k delta t delta y at the wall of the order of, I mean, okay, so if I write at the wall this is equal to h into Ts minus T infinity. Now if I do the order of magnitude analysis, this will be delta T by delta naught, okay, and this will be of the order of h delta T. That means here we are getting h delta naught by k is of the order of 1. That means my Nusselt number is of the order of L by delta naught, right? And so I am getting what? I am getting that my Nusselt number is of the order of L by delta naught. So L into delta naught to the power minus 1. That means L into delta naught is now what? The order of delta naught? G beta delta T. G beta infinity. Okay, I will write this as delta T infinity. Okay, or just only delta T. Okay, delta T infinity is fine. This alpha infinity L. Yes, everything is fine. Into whole to the power minus 1 by 4, right? Into minus 1, that will be plus 1 by 4. Okay, so now what I can do is I can just what I can do, I can take this 4 inside of the bracket, right? And I will get L to the power 4 delta T infinity by this L 4 to the power 1 by 4, and now I will get G beta delta T L cube by, okay, nu square, okay, into uh, what else, nu by alpha. Clear? Whole, so this whole to the power 1 by 4 and this whole to the power 1 by 4, this I am getting. So now this is a non-dimensional number and known as Grashof number based on infinity, or Grashof number we write based on the length L, and this is Prandtl number to the power infinity. And further, this Grashof number into Prandtl number is equal to Rayleigh number based on the length L whole to the power 1 by 4. Okay, that means for, okay, Prandtl number much greater than 1, my Nusselt number based on L is of the order of Rayleigh number whole to the power 1 by 4. Okay, and actually we will get something like this. Nusselt number is equal to some constant C into Rayleigh number whole to the power 1 by 4. So we will find this constant C when we will be solving for the exact solution. Okay, exact or approximate solution. Now likewise, if you do here, you will get that here I will just do a small manipulation. If I divide by L, okay, so here also I have to divide by L, right? So into 1 by L. So if I have to put this L inside the bracket, then I have to do what? I have to do it as L to the power minus 4, right? L to the power minus 4, that means this L to the power 4 will be there, and this will be L cube. So you will be getting from this that delta naught by L is of the order of, again, Rayleigh number whole to the power minus 1 by 4. I mean, this has to be the thing, because we got that this is of the order of Rayleigh number to the power 1 by 4. Okay, so now this was our engineering purpose to find the heat transfer coefficient and thus the Nusselt number. Clear? But now let us have some intuition. As engineers, we have, I mean, we take care of this intuition very much. Okay, I mean, we must have the intuition of telling about the results, okay, before solving the problem, at least for, I mean, what will be the nature of the velocity profile. Okay, so I have already talked about this heated layer thing, right? I have talked about this heated layer thing, and I told that here we have this heated layer within which we have this valid temperature gradient. So this is Ts, and at this side we are having T infinity. So in this region the temperature gradient is there. But now I am saying that my Prandtl number is much greater than 1. That means my nu is much greater than alpha. So this is what, this we all know, that momentum diffusivity, and this is what thermal diffusivity, right? So if my momentum diffusivity is much greater than 1, so then what will actually happen is that see, this layer is the cause of the natural convection where the temperature difference prevails, right? So this layer is actually called the driving layer, okay, the driving layer. Clear? Because it is driving the flow. But even if the temperature gradient and thus the buoyancy force is 0 at this point, I mean it has got diminished at this point, in this region there is no temperature gradient, thusly no buoyancy force, but still there will be fluid motion because we have a very high momentum diffusivity. So we expect that if we have this of the order of 1, that is this alpha is of the order of nu, then the velocity profile would be something like this. Okay, that at this point, because I don't have the thermal effect, then the velocity will be also 0, because these two are of the same order of magnitude. So thermal diffusivity means what? Up to which the velocity, up to which the temperature difference prevails. So it is dictating that at, I mean thermal diffusivity means that up up to up to which point the temperature effect will penetrate, and momentum diffusivity means up to which point the velocity effect will be felt. Okay, so these are very rough things, but you need to have these intuitions. Okay, I hope that I can convey you. If I cannot, then please comment. Okay, so here in this case, because alpha is very low compared to nu, that is why even after the delta t has got diminished, but the velocity boundary layer will be larger than the thermal boundary layer. Okay, so now the velocity will have a maxima here and it will go down to 0 here. I am not saying that this is a symmetric curve. Okay, and the temperature will be something like this. Okay, so it will have a maxima here and it will be 0 here. So this is the temperature profile. Okay, and this is the velocity profile. Clear? And obviously this layer is termed as, okay, driven layer. Why? I have already told that in this layer temperature difference is there, that means density difference is there, that means buoyancy, the driving force is there in this layer. That is why this is the driving layer, but here there is no driving force. Here there is fluid motion because of this layer. The momentum of this layer has been diffused to this layer because of this large momentum diffusivity. Okay, now see, in this layer buoyancy force is very important and it is competing with the viscous force. As the Prandtl number is greater than 1, I have shown you that the inertia force is negligible in the layer, in the heated layer. Okay, so actually this is our heated layer now. Okay, and in this layer we don't have any buoyancy force. So in this layer inertia force will compete with the viscous force. Okay, and after this point both the temperature and velocity are at the reference state. So velocity is 0 and temperature is there. Okay, now I have a homework for you. Can you tell me that We have taken the boundary layer approximations, but what is the basic difference? I mean, can you tell me a basic difference in terms of velocities? Okay, I will ask you the question directly. So here my y component is this, right? This is y, and x component was this along the plate, right? So can you tell me the y component of velocity v? Okay, so can you tell me that v at delta velocity, that is velocity boundary layer, okay, v at delta velocity, this will be what? Here this will be what? I mean, in case of so you have to find this. So for boundary layer, so if this is a flat plate and the fluid is flowing like this for a forced convection flow, okay, then we have a boundary layer. So here also we have v at this point at the edge of the boundary layer. So what is the difference between this v and this v here, the y component of the velocity? Okay, you have to tell me the difference. You obviously you can't tell any kind of value, you have to tell me the nature of this v. This v is positive, I mean, if this v is positive at upwards, you can say that this v is going outwards, this v is going inwards or outwards, like this. Okay, so I think I can convey you the question. So this is your homework, and in the next lecture I will explain this difference in v. After that I will go to the next cases, Prandtl number less than 1 and of the order of 1. Until that, goodbye, take care, and thank you.